Good morning, ladies and gentlemen. It's a pleasure to be here with you today. First of all, I'd like to introduce myself. I'm Marwa Dahmani from National High Schools of Mines and Metallurgy, Annaba, Department of Material Sciences and Engineering. Today, I'm going to give a short presentation on an investigation of the mechanical and microstructural evolution of new generation beta-type titanium alloys for biomedical implant application. My presentation is divided into four main sections: introduction, alloys preparation method, overview of the process parameters effect on structural and mechanical evolution of beta-type titanium alloys, and finally, conclusion. Titanium commercially pure alpha type and its alloys, alpha plus beta type, are currently favored as orthopedic implant materials due to their superior biocompatibility, corrosion resistance, and strength to weight ratio. However, as they have a greater elastic modulus than human bone, these alloys may be biomechanically incompatible. A difference in elastic modulus between implants and bone can result in excessive stress shielding, which can lead to implant failure prematurely. Furthermore, some widely used titanium alloys are susceptible to dangerous ion release, such as aluminium or vanadium. The production of these ions following long-term in vivo implantation has been linked to a number of issues, including Alzheimer's disease. As a result, there is an urgent need to create new titanium alloys with lower Young's modulus and no harmful compounds such as molybdenum, niobium, and zirconium. The use of titanium beta alloys with a low modulus of elasticity, high strength, and beta corrosion resistance is the appropriate solution. The current area of research is on the creation of beta-type titanium alloys with a reduced elastic modulus and improved biocompatibility. The aim of this study is to investigate the effect of added element content and centering temperature on the structural and mechanical behavior of beta-type binary and ternary titanium alloys manufactured by mechanical alloying method from elemental powders of titanium and other elements stabilizing the beta phase for orthopedic application. The material investigated in this study is a non-structured beta-type titanium compound, binary and ternary for biomedical application. The powder's properties are listed in the table below. The following diagram shows the various steps involved in the material's synthesis. The effect of centering temperature. Concerning titanium niobium alloy, the centering temperature increased, the average pore size and crystalline size dropped steadily, reaching the lowest value of 41 nanometers and 27 nanometers at 1100 degrees Celsius, respectively. Furthermore, higher centering temperature increased the relative density, hardness, and Young's modulus of titanium niobium alloys. Grain refining was associated with the improvement in mechanical characteristics. In the case of titanium niobium zirconium alloys, morphological characteristics reveal that as centering temperature increases, the average pore and crystalline size decreases. However, at a temperature of 1250 degrees Celsius, the relative density of the centered symbols is the highest, at 98.7%. Because of the high central temperature, the material has a high relative density and a closed porosity. It can be seen effect of added elements contained. It can be seen in figure 1 that the beta phase increases as the molybdenum content increases, and all alloys consisted of alpha and beta phase except for titanium 20 molybdenum alloy that exhibits a single beta phase structure because molybdenum is an element that serves to keep the beta phase stable. Figure 2 shows the evolution of pore structure characteristics, total porosity, open and closed porosity of titanium molybdenum alloys as a function of molybdenum concentration. As presented in the picture, the total porosity and the open porosity decrease as the molybdenum content increases from 0 to 20. But the closed porosity increases as the molybdenum content increases. Titanium 15 molybdenum and titanium 20 molybdenum alloys also had consistent porosity and thicker pore walls, which helped to improve their mechanical characteristics to satisfy the demands of biomedical implants. To summarize, the influence of central temperature and additive elements contained on the structural and mechanical behavior of binary and ternary titanium alloys for biomedical implant application manufactured by mechanical alloying method is reviewed briefly in this presentation. The following conclusion can be drawn. Porous titanium alloys prepared by mechanical alloying had gained much attention. The mechanical alloying can be used to produce a finer grain structure having higher mechanical properties, since they may produce titanium alloys with lower elastic modulus similar to the bone. The continuous increase of both central temperature and alloying element content provide to modify the alloy microstructure and enhance mechanical property, improving the hardness and decreasing elastic modulus up to an optimum value of alloying element contained and central temperature that presents the best structural and mechanical characteristics of binary and ternary alloys. Thanks for your attention.